Hello everyone. So in this video, we will be talking about the situations that we have to face if at all we have to implement an FIR filter and an IIR filter in a fixed point processor where we are bound to use a Q notation. So usually it is Q15 notation where the maximum possible number and the minimum possible numbers that you can represent range from -1 to +1. In such situation, what you have to do is while giving the input itself, you have to scale down the inputs, and then afterwards, once you get the output, you will have to, scale up once again. Okay. So, but what is the factor exactly by which you have to scale down or scale up? That will be seeing here. Okay. So filters can be FIR, filters can be IIR. So lattice filter structures are out of the scope of at least this particular topic now, as we do not have much time. We will discuss simple FIR filter. What will be the scaling factor? So you have to scale the input and you have to scale the impulse response. So there are the impulse response coefficients. Okay. And in IIR filter, the kind of scaling that we use differs between direct form 1 and direct form 2. Okay, let us see. Let us start with simple FIR filter and what are the issues. So to avoid the overflow in an adder, they say we can scale the input down by factor s, which can be safely determined by this particular equation. So it is I max is the maximum amplitude of input in Q format. Okay. So why they are talking about maximum amplitude of input? Say you are trying to read some of the very minute values where your maximum input that can you have, if at all it is very less, say 0.003 or 0.01 or something, and the filter order is also something like 8 or 16 or 32. In that case, we may not need to scale it because the total summation of a convolution or the entire thing may not exceed 1. So only if there is a threat of an overflow or an underflow, then only we need to scale. That is why the formula. Okay. So what does the formula say? So depending on the impulse response, see here we are trying to find out the scaling factor for the inputs, which is determined by the impulse response. Okay. So we are trying to find that worst value of impulse response, worst value of input. Okay. We will assume maximum values here. Okay. Now see the formula is magnitude, all the coefficient magnitudes added multiplied by the maximum amplitude possible. Okay, that gives us the scaling factor for the input coefficients. Okay, and if this is the case, then your adder output is going to be something like this. Okay, then what else? Now what about the scaling factor for the coefficients? The scaling factor, the coefficient b. Okay, so what it should be, this should be, since it is getting multiplied. Okay, so the inputs whatever they are there, after scaling they will be adding up. That is why we took care. Whereas the coefficients of the impulse response, they will simply multiply. That's why we need to only make sure that the total number, the coefficients, none of them are exceeding 1. Okay, none of them should exceed 1. Okay, so what's the value needed? So this particular value b should be such that it should be convertible in Q format. That means if at all it is a Q15 notation, this particular value should not exceed 1. Next important thing is s and b cannot be different values. Okay, it's a constant. Okay, here also b, you cannot have different coefficients for different scaling factors for different coefficients. It should be constant. The trick is, in the beginning you scale it by factor 1 by s. That means you divide, and then afterwards, once before getting the output, you once again multiply. Same is the case with the coefficients of the impulse response. Same is the case with coefficients of our FIR filter. So how are you going to do this thing? Actually, we are having a digital circuit. Say suppose I have this number 110 with 4 digits at my disposal. Suppose I want to scale it by factor 2. I will just have to shift it to the left side by one location. If at all I want to multiply it by 4, okay, if at all I want to divide by 2, I will shift it to the left. If at all I want to multiply it by 2, I shift it to the right side. So to have that particular freedom, to have this particular freedom to be able to do multiplication by simple shift operations, rather, I will always shift. Say I want to have a shift factor of say 1.56. Okay, say the shift factor that I exactly need is say 1.56. I would rather shift it by a factor 2 because the process is easy. Suppose I want to divide some number by factor say 3.1. I would rather go and divide it by factor 4. Okay. Hmm. So this will be the approach. So all the numbers usually they will be converted to nearby powers of 2 so that the entire purpose is served also. Okay, so let us see an example. Let us see an example here. As you can see, here is a simple FIR filter. 0.93 and zero point 0.9. They are the values of the impulse response. So here first the scaling factor. And there is one more thing. Only occupies 1/4 of the full range for a particular application. So they said that for a passband gain of 4, or this doesn't matter. Input range occupies 1/4 of the full range. Okay. So that is where this 1/4 factor Imax comes in. Okay, then afterwards this is the formula, the impulse responses. Okay, the impulse responses, and this particular number 1/2, 1.2 comes in the scaling factor for all the inputs, so that even if my inputs they never exceed, so that my input x of n they never exceed 1.2, that thing is taken care. Okay, so see here, so even though 1.2 is the scaling factor, so this could have been either the nearest powers of 2 are either 1 or 2. If at all it is 1, it doesn't serve this particular purpose, so we'll go to the next higher number, which is 2. That is why scaling factor of 2 is chosen. What about the scaling factor for the coefficients? For the coefficients, the scaling factor is chosen such that you can see here the coefficients are 0.9. This can be represented using Q15 notation. 3 can be represented using Q15 notation. Zero point 0.9. Wait a second. 3? No. 3 cannot be represented using Q15 notation. That's why what we'll do is we'll scale all these coefficients by factor not 3 but 4. Okay, so the scaling factor for the filter coefficient shall be 4. The scaling factor for the inputs shall be 1.2 rounded to 2. Okay, so this is the thing that we need to take care in case we are trying to implement an FIR filter. Now what's the deal with a direct form 1 IIR filter? If at all you want to, wait a second. Okay, so what is it with the FIR filter? Sorry, an IR filter. As I told you, IR filter can be direct form 1 or it can be direct form 2 filter. Even though direct form 1 and direct form 2 give you the same response, now maybe it is due to the scaling. Now we cannot have the same kind of treatment for scaling here. Okay, anyway, let us say direct form 1. Okay, so here also it's the same thing. The coefficients here also you have to decide on the scaling factor S in the beginning, upscaling here. Then you have to identify this particular factor here, which should help us in representing the coefficient in Q format. So how bad this can be? There is a catch, because these coefficients B0, B1, Bm and all are determined by the impulse response, whereas in an IR filter we do not know exactly what's the kind of impulse response that we are going to get. Let us see an example. Here is a simple IR filter, 2 into x of n plus 0.5 into y of n minus 1. We need to determine the impulse response. Okay, we need to determine the impulse response so that we can identify the scaling factor. Why is it so? Let me take you back to that particular equation here. This one here, S, right? So as for this particular equation, we need to know the impulse response. Okay, so let us go back and let us see, is it that complicated? So here we have a very simple problem. Impulse response equal to y of z by x of z, C2 y of x of z coefficient, then 1 minus 0.5. So this is 2 into z divided by z minus alpha, alpha to the power n into u of n. Okay, so the impulse response here is 2 is a constant, 0.5 to the power 0, 0.5 to the power 1. So this is simple. 2 happens to be constant. So what is the summation? Summation 0.5 to the power n going from 0 to infinity, 1 divided by 1 minus alpha. So 2 into 1 divided by 1 minus alpha. Okay, 1 divided by 1 minus 0.5. That's where we got this impulse response. Of course, there was the scaling factor 2. The coefficient 2 was there anyway. The constant 2 was there. Then they say maximum input is 0.25. So that is why we divided it by 0. Multiplied, sorry, by 0.25. 0.25 is Imax. 2 is the coefficients. 1 divided 1 by alpha gave you the h of n value, not h of n value, actually is a summation of all impulse response coefficients. So from that, s equal to 1 has been derived. Okay, so scaling factor is 1. Let us see. Scaling factor is 1. What else now? Now one statement is made here. We do not, so hence we do not need to perform input scaling. Fine. However, we need to scale down all the coefficients to use Q15 format. What is this? Why scaling all the coefficients? Because here in this particular example, wait a second, in this particular example, 2, okay, 2 you can see has exceeded 1, which is the Q notation. So usually the maximum number that you can represent is 0.999 or something like that. Okay, 0.99 or something like that. That is why we'll go for a number which is bigger than 2. So we'll use for this particular thing coefficient of 4. Okay, so we have an expression here where our c, the coefficient c equal to 4, and the other coefficient is what's the other coefficient? 1. Okay, so the figure remains the same. Okay, c equal to 4, s equal to 1. So once you are done finding the coefficient, you better draw this particular direct form implementation also for completeness. Okay, now let us see how it is different for direct form 2. The reason why it becomes different for direct form 2 is probably this one. This is where it gets deviates. I don't know. Let us, you know, adhere to the textbooks and let us have this particular method. Okay, let us have this particular method. For direct form 2 implementation, what do we do is we will assume an intermediate value W of n. Okay, we will assume an intermediate value W of n in the beginning, and we'll treat them as two separate things. One are the forward paths or the feed forward paths, and then we'll treat a different set for feedback paths separately. Okay, let us see here. So W of n in terms of feed forward path gives you, from here you directly come here, the meaning doesn't change. The meaning doesn't change. W b naught x of n minus a1 x of W of n minus 1. Wait a second, let me rub this particular thing. Okay, okay, so W of n in terms of x of n. Okay, so you can see W of n 1, 2 and 3. Okay, so W of n terms of x of n, and then we'll interconnect this with y of n to get W of n, then the feed forward paths. Okay, then the feed forward paths. So let us see the kind of treatment that we have here. We are treating this equation in a different manner to find the scaling factor, and this expression we will have a separate approach to find the scaling factor. Let us observe carefully. For the first expression here, for the feedback paths, what we will do here is, let us see a numerical itself. Okay, so first expression including the feedback path with x of n term, what we will do is we will find the impulses, the transfer function a of z. We will find the transfer function a of z. Okay, and for this feed forward path, okay, which is on the right side, we will simply scale it based on the highest value. Okay, so here how do we find now, how do we find the impulse response? So they have in the textbook taken IMPZ function of the MATLAB. So here I think I would suggest you to go for the long division method and try to find 1 to some 4 coefficients. Okay, long division method, 1 plus 0.5, 1.52 z to the power minus 1 plus 0.64 z to the power minus 2, or you can also split it into 2 parts using partial fractions, and then you can try to find the coefficients. Okay, so this one anyway we cannot do it, but the some number turned out to be number has turned out to be 10.4. 4, we can remember the number at least. In case we get lucky, if the same problem pops up, then who knows, we can substitute this particular number. So 10.40. So what shall be our scaling factor? Nearest one is 8, would give still give problems. 16 will give you power of 2, which can be directly achieved using a simple shift. Okay, now what about the second number, by the way? So for the feed forward path, okay, for the feed forward path thing, we just have to, we need not find the impulse response, we just have to find the largest number. So 1.49, so we have to scale the entire thing by 1.49. So nearest number is 2. Okay, nearest power of 2, sorry, is 2. So wait a second. Yeah, so here, next page. So there, that's that. Okay, so that's it. So scaling factor for the inputs is 16, and a equal to 2 is chosen. What about b, by the way? What about b? What about b now? For b, the sum of three numbers should not exceed 1. The sum of these numbers should not exceed 1. So taking that into consideration, I think this is sort of, confusing us. But 1.49 plus 0.75 plus 0.75, I think 4 was the nearest match, and it fits the requirement. Okay, so 3, 4, yeah, almost there. So B is 4. So little tricky here. So there are three scaling factors. So 10 point, the fraction thing rounded to 16. Then we got 2. So 2 from the expression directly, 2 from the expression directly. Then afterwards, the sum was considered, and we got 4. Okay, that's about the FIR implementation. So this is, I think, very simple topic. It's mentioned exclusively in your syllabus, and hopefully you do not have to write any programming or something. So you can expect this questions. Okay. So that's it. That formally ends this particular chapter. Thank you.